And we now go to the last talk of today with Declan Bartlett. Go ahead.
Thank you. Yes, I'm Declan Bartlett. I'm a postdoc here at the IAP, and I'm going to be talking to you about a project I've been working on with these people, which is somewhat cheekily called the terms Eisenstein and Hu missed. So the idea here is we're wanting to produce a symbolic emulator for the matter power spectrum. So the reason for this is, as we've probably heard a few times today, this is what you tend to do in a cosmological analysis many, many times. You start with some set of cosmological parameters, you then plug it into a Boltzmann solver, so CAM or class, and then out come some outputs. So this may be a power spectrum, it might be a derived parameter like sigma 8, but whatever it is, if you're doing an MCMC, you need to do this many, many times. And that's why people have come up with emulation techniques, because you don't really want to do this many, many times because it's too slow. So here's a lot of emulation techniques that exist and are used now, numerical in some sense. So this is either using a neural network-based approach or a Gaussian process-based approach in order to produce P of k as a function of cosmological parameters. But this wasn't always the way. For a long time, and people still use it, we had Eisenstein and Hu. So this is an extract from the 1998 paper. And essentially, it just uses physics that Eisenstein and Hu knew, and lots of constants. And you're able to get a pretty good fit to the matter power spectrum without any of these fancy deep learning techniques. When I say a pretty good fit, I mean to a few percent. What's nice about this, you can interpret it, so you can look at each of the terms and understand what's the effect on the power spectrum, but also why it's there, what physics produced it. It's easy to incorporate physics. I mean, it's built on physics. It's very portable and it has longevity. It's just a few lines of code. If you sit and write it down, you don't have to worry about, oh, my version of TensorFlow became outdated, so I now need to transfer all my weights, my architecture across. You just can copy and paste what was before. You can it's easy to change programming language because you don't need to write any wrapper or install some wrapper. But the problem is it's not accurate enough. It's only accurate to within a few percent if you're using the Eisenstein and Hu formula. So what we want to do is see if can you improve this and get it to sub% accuracy. So to do this, we're going to be using symbolic regression, and in particular, a genetic programming code called operon. So operon is very fast, memory efficient, and it's written in C++, so it is very quick, and it's performed very well in previous benchmark studies. So we're going to stick to just lambda CDM for now, and we're going to do the redshift 0 linear matter power spectrum varying 5 cosmological parameters, so AS, omega m, omega b, h, and ns. And I'm going to have a very small number of simulations. So I have 100 training and 100 validation cosmologies on a Latin hypercube. And I'm going to compute what I call the truth with CAM. So to start with, let's do the first one of these steps. Let's see if we can go from cosmological parameters to a derived parameter in a simple symbolic expression. Because normally what would happen is if you want to vary sigma 8, but you need to run CAM, you need to change AS as the input, but you actually care about sigma 8. So what you would normally do is you'd pick an AS, you'd run CAM, you'd see what sigma 8 came out, you'd rescale AS by the ratio of the sigma 8 squared, and then you can rerun your Boltzmann code. But for the cosmologies we tried, we find that this expression does very well. So we can get a root mean squared error across the cosmologies we tried of just 0.3% on this, which is pretty small compared to the error you would actually get on sigma 8 if you measured it. And it's one line. So it's pretty fast and pretty portable. So we were quite pleased with this. But that's a somewhat easier task, because there I'm just predicting one number. Now I want to predict a power spectrum that depends on K as well as the cosmologies. So here, to make our life easier, we might as well use things that people can already do. We already know that Eisenstein and Hu works very well and is commonly used, to within a few percent. So we factorize our power spectrum like this. So we take Eisenstein and Hu, and then we multiply it by just some function of k and cosmology. So that contains all the physics. I've crossed out BAOs because we're actually going to use the zero baryon Eisenstein and Hu, so that our residuals look a bit like this. So here I'm plotting log f as a function of k. Here's for the Planck 18 cosmology. And what we want to do is we want to learn log f. So here, as a function of model length, here I'm plotting the error we get for our training and our validation. And you see we need quite long models. So we need a reasonable number of terms in our expression. Something of order 70 to 80 seems to give a good fit. So we go for a model length of 77 as our favorite. And this contains some terms that are physically interpretable. For example, one of the terms our symbolic expression spits out has a cosine term that looks like this. So you can see that there's some omega matter dependent phase shift and some omega baryon dependent frequencies. So this is talking about the BAOs. And if you plug in the right parameters, you see that the coefficient of the k there is just at the sound horizon. And that's what I'm saying there. So if I plot the fit over the truth, this is for the Planck 18, which wasn't in either training or validation. This is the what you get. So it's almost, there's no difference by eye. And if you vary cosmologies across a reasonable range, you see that you can get sub% accuracy for all k and a root mean squared error of point a few percent. So to conclude, here we've made a symbolic emulator for both P of k and sigma 8 as a function of other cosmological parameters. And then I thought I'd end with like a provocative point, because it's a debate workshop. And the question here is like, do you really need a neural network for a problem like this? So there are clear advantages to having symbolic fits. Not all problems are simple enough to do this, but the longevity, the interpretability, portability, and the much smaller number of parameters I see as advantages. So thank you, and I'll take some questions.
Thanks a lot, Declan. So we'll take a few questions for this last talk of today. Any question in Paris? Agnes, please.
Very interesting. So with emulators, I think one of the issues is that we have to often retrain them, like to the number of K you want, number of Z, like the precision you want. And is that, in this case, is that something you will need to do as well? Or not? Like, maybe the question is how much it depends on your training sets? Like,
yeah, so for this, we picked the same training set as the Euclid emulator in terms of prior widths and K range. So yes, the problem is obviously if you go, like any emulator, if you go outside the range of K, for example, that it's trained on, then you might get some weird effects that are due to extrapolation. Luckily here we know that, well, definitely at low K, we know what the analytic form is, so you can just turn this correction off. At low K and at high K, well, we're already doing linear, so unless you're having some nonlinear correction like halo fit that goes from linear to nonlinear, you probably wouldn't go being high K than we've used anyway. We went up to a K of 10, so it's very high. But yeah, that's the same as any emulator. I suppose here, at least you can see by eye what terms are going to be problematic. But yeah, say you wanted to add in like f of r like in your talk, then you want to redo the whole thing, or you might just want to learn a hopefully small expression that can be used as like a boost, or like to shift what's the ratio between the f of r power spectrum and the lambda CDM.
very interesting, thanks.
Okay. Any question in New York? New York?
Do you have any New York questions?
You must be hungry. Sorry.
We have one here, yeah.
Very nice talk, Declan. So did I understand right that you need like 70 terms to get the sub% precision?
So when I say 70 terms, I mean 70 combinations of symbols. So maybe if I can show the slide, I can show the expression. I didn't want to scare people. So it's that, which I think if I put it up initially, it was very scary, but it has, the first line just has some scaling that just moves the line up and down. The second, then the remaining 4 terms are just all multiplied by cosines. 2 of them have are linear in case, so it's just a BAO with some frequency that depends on omega b. Then there's another one that just provides some overall modulation that has the 1 over 1 plus b15 k squared. So this is what I mean when I said 70 terms. So it has like 30 parameters, 35 parameters, something like that, 37 parameters. But that's what I mean by 70 terms.
So can I ask another one?
Yes.
That's parameters. We have a question here in Paris, and then back to New York.
Hi, thanks so much. Do you enforce any differentiability or integrability constraints in your equation search? So what's nice about neural networks, right, is that you get from big data space down to potentially smaller summary space, and most of the time the gradients are pretty stable through those networks. So obviously your analytic expressions appear differentiable, but it could be you find one that encounters a divide by 0 somewhere, right? If you're only searching for the f of x and not the the df of x or the integral.
Yes, I suppose that so we haven't verified the gradients on these. That would be straightforward to check. But yeah, I guess this could happen. We haven't enforced anything along the equation search to do this. So it'd be worth checking.
I guess it would just sort of prune your search space, wouldn't it?
Yeah. So you could either prune it during it or during its model selection procedure. You pick one that's reasonable.
So we're going to go back to New York to see whether there is a very last question before concluding this session. New York.
Yeah, thanks for this talk. I'm Jamie from Berkeley, and I was just wondering if it's correct that you didn't include the radiation or the neutrino parameters in the symbolic regression, because that's where almost all of the effort of the Boltzmann code is actually going computationally. So I was just wondering if you had looked at that.
We went for simplicity first. So we went for, let's just do cosmological parameters with 0 neutrino mass. But it would be looking in the future to go to both nonlinear P of k and to include parameters such as effects of neutrinos.
Okay, I think that this is going to be the last question for today's session. I would like first to please thank all of the speakers of this session and of today.